Ayush Kumar Tyagi. Uh, I'm working on automatic detection and grading of celiac disease. I'm working with Professor Mosam and Professor Pratosh AP. Celiac disease is an autoimmune disease caused by consumption of gluten. It is estimated that 1 in 100 people are suffering from celiac disease in India. A common way of identifying celiac disease is through duodenum biopsy. There are two components which are important, villi and crypts. Due to celiac disease, people observe a reduced length in the villi, which result in malnutrition in the patients. If you can see, there are two components. One is villi and the other one is crypt. As the severity of celiac disease increase, there is an increase in the IELs in the tip of the villi and eventually reduction in the tip of villi. There are three steps in identifying uh, celiac disease. First one is identification of the interpretable region. The interpretable region is the region where there is a proper epithelium layer and the villi are in good state. Second one is within the interpretable region, you identify the tip of the villi, and in the tip of the villi, you count IELs, interepithelium nuclei, and you compute the Q histology score, that is, number of IELs per 100 epithelium nuclei. If the Q histology score is greater than 25, then there are chances that person is having a celiac disease. The third step is basically the measurement. In measurement, you compute the length of villi and crypt. As the severity of the celiac disease increase, the villi length reduces. And using the villi length, the celiac disease is graded into various categories. In the previous uh, meeting, we discussed, we talked till cell counting problem, where we identified that there is a tip of villi, there are two type of cells, IELs and the IELs and epithelium nuclei, and we compute uh, interepithelium Q histology score for them, that is IELs per 100 epithelium nuclei. We know that the manual counting is tiresome and often lead to inter-observer variability. So what we propose is, can we actually learn the attribute of cell like the pathologist to mimic the workflow of the pathologist. Pathologists look into few characteristics like IELs are circular, darker and smaller in size, where epithelium cells, which are like elliptical, lighter and larger in size. We incorporate this information into the model and penalize the model to when the model does not focus on these type of attributes. Here is the complete architecture which we have seen last discussion. Additionally, I have worked on box cell, that is leveraging SAM for cell segmentation with box supervision. In this problem, we have used a bonding box to get the segmentation mask. In so this paradigm is basically a weak supervision paradigm. There are two components, ITD and ITS. In ITD, the model there is a detection model which predicts bonding boxes, and those bonding boxes are used to predict segmentation mask. There is ITS where you have a segmentation model which predicts segmentation mask along with and we compare it with the ground truth segmentation mask. This ITS is trained on the segmentation mask which was generated using ground gold bonding boxes. Gen- Here is the complete architecture. We basically try to merge the complementary strength of ITS and ITD using a ILP formulation. In the previous year, I worked on measurement based celiac disease identification. That was the third step. We have formulated the problem as polyline detection. We can see that like in the first uh, column, if we want to compute the length of a villi, you cannot do it using a bonding box because uh, in order to measure the length, you can actually measure along any of the major axes, and in this particular case, the diagonal is not accurate representation of the bonding box. Similarly, segmentation mask has its own challenges, like there is a discontinuous segmentation mask in most of the cases, and if there is a discontinuity, we are not able to recover the complete length. So instead, we formulate the problem as the polyline detection task, where there are multiple points to a line, and we predict the line. The data set consists of two type of annotation. One is the polyline annotation, the another one is the segmentation based annotation. In the segmentation based annotation, we have villi shoulder and crypt border, because we observe that the crypts are very difficult to identify. So directly predicting crypts is very difficult. So instead, what we do is like we predict the two boundaries uh, between the starting point and the end point of the crypt. So for what measurement does is, for a biopsy, it predicts a, a certain point. It predicts 6 points: xy, x1, y1, x2, y2, x3, y3. What we have observed is the crypts are very difficult to identify. So we use the segmentation model, which is trained to segment the villi shoulder and crypt border, and we pass this information to our detection model. In order to pass this information, we have two feature extraction blocks, one for image and one for segmentation mask, and we have a feature merger block which merge the information coming from images and the segmentation mask and provide to the object detection module. We have observed that there even during training, it was like, as the predictions are very good, but when we do the inference, there is a shift in the quality of prediction. So what we do instead is we use two segmentation masks, one coming from a strong segmentation model, the other is coming from the weak segmentation model, and we do a feature mix up to get a combined feature representation, and then we feed this information into the feature merger block that merge it with the imaging feature. We observed that like using this kind of like feature mix up improved the overall performance. These are the qualitative performance of the MeasureNet. You can see that it is way better than the segmentation based approaches, and even the closest baseline, which is LETR. Qua- Quantitatively also, we are like way better than it's the closest baseline. We additionally compare the classification performance. We see a improvement from 81 to 82 in term of precision, and 73 to 82 in term of uh, like accuracy. In the grade uh, classification, we see an improvement from 70 to 81%. Another part of my work is designing a software. We are working on creating a software that will help pathologists to analyze the slide and uh, like improve the prediction of these models. There are three parts here as well. First one is basically the interpretable region. You identify the interpretable region. It is denoted by a bounding box. Once the interpretable region is identified, we pass it to the measurement module, which predicts the length of crypt and villi, and also provide the average villi length, average crypt length, villi to crypt ratio. Then we upload a 20x image where we identify the tip of villi, and in the tip of villi we identify the type of cells, that is IELs and the epithelium nuclei, and compute the Q histology score. The next is basically generating the report. The generated report looks like this. It has the case number, the date on which it is generated, whether 4x images uploaded, 20x images uploaded, and these are the statistics of whatever the model has computed. We also provide information how we are calculating the Q histology score or the Marsh grid score, and additionally there is a disclaimer, there is a doctor name and the place where the doctor can sign. In future work, we are trying to improve the software by providing a better visualization. Like we have seen that in the previous slides, the cells are represented by the bounding boxes, and it is very difficult for doctors to identify whether the predictions are correct or not. So instead, we use dot representation, and once you hover over the dot, it will automatically turn into the bounding box. Additionally, we are trying to provide the confidence score of the model. The green are the high confidence, the red are the low confidence scores. Additionally, there is a filtering based on the confidence. So the red ones are the high, uh, very low confidence cells, and doctors can only look into this. It will reduce the overall time of the uh, diagnosis. Additionally, we're working on generating histopathology slide images using the text prompt. We have the annotations corresponding to many slides, and we are trying to use the annotation to generate more slides. It will make our modules more robust, and we are hoping that it will improve our accuracy as well. Thank you so much.